Okay, let's do another problem from chapter 8. A student sitting on a stool rotating at a rate of 20 RPMs holds masses in each hand. That's what I've drawn here. He's going at 20 RPMs. Rotations per minute. When his arms are extended, the total rotational inertia of the system is 4.5 kilograms meters per second. He then pulls his arms in close to his body, reducing the total rotational inertia to 1.5 kilograms per meter squared. If there are no external torques, so no friction, no air resistance, what is the new rotational velocity of the system? So how fast is he going now? Okay. So he's here, has his hands out, and then pulls them in closer. You've probably done this at home or at a store or something where you've had a bar stool. You can hold your legs and arms out and then close it, pull them all in, and you notice that your speed changes. I'm not going to tell you what happens whether you slow down or speed up, because you can solve that with by doing this problem. But I'm going to show you some of the math behind it. So let's review some things. L is the angular momentum. I is the rotational inertia, and this funky W is rotational velocity. Now the L, the momentum, is conserved. There's no friction or anything like that, so the momentum here in scenario 1 is the same as the momentum here. So that's why I wrote L initial is equal to the L final. Well, momentum is equal to, and you've probably seen this in the notes or the book, your rotational inertia, I, times your rotational velocity. Okay, so this this momentum initial is equal to your initial inertia and your initial rotational velocity. The L final, your final momentum, is equal to your final inertia times your final rotational velocity. This is the thing we're wanting. We want this right here. Let's write out the things we know what we want. Let's write out the things we know. We know the initial inertia. We know the initial angular rotational velocity. Let's try writing this down. This is 20 RPMs, rotations per minute. This is, let me see, 4.5 kilograms per meter squared. And our final, I final, is 1.5 kilogram meter squared. We're looking for, this is initial, looking for the final rotational velocity. Okay, so we have equations, we have our knowns and unknowns listed. If this Li is equal to this, and this Lf is equal to that, here I'm saying Li is equal to Lf. So if I can say Li equals Lf, I can say the initial rotational inertia times the initial rotational velocity is equal to the final inertia and final rotational velocity, right? So I said this is equal to this. Well, if that's true, then this is equal to this. No, it keeps circling stuff here. So if these two are equal, that means the blue is equal. That's what I'm trying to get across here. Alright, so we're going to use this equation because I can fill into this equation. I don't have the momentums. You can solve for the momentums, but I'm going to just use this equation. I want the WF by itself. It's not really W, but I want the rotational velocity by itself. So I'm going to rearrange the equation by dividing by the final rotational inertia on both sides. So now I have I times the initial divided by the final rotational inertia, boom, equals that. Okay, that's the thing I wanted by itself. Now it's by itself. All I gotta do is plug in the numbers, and let me do that. That's right, with the numbers in there. 4.5 kilogram meter squared times 20 RPM divided by 1.5 kilogram meters squared. Okay, if you're wondering, okay, what's my unit going to be? Look, kilogram meter squared divided by kilogram meter squared, those cancel out. The unit you have left is RPM. So take 4.5 times 20, divide by 1.5, and that's your final rotational velocity. And make sure that has the unit of RPM.